Good morning, everyone. I hope everybody's doing well today. Again, we're enjoying our nice spring weather. I would say that we all should enjoy as much of it as we can, even though most of the time we're inside, because it always gets warmer during the summer. But I'll be the first to say I don't mind the warm weather too much. I think Professor Ron would rather be a little bit warm than cold, but I'm sure everybody has their own preference where that is concerned. Um, my family grew up in North Carolina, and my brother and his family are still in North Carolina. My mom and her husband are still in North Carolina, but my sister and her family are in Montana. So she has actually spent most of her life in really cold climates. So she's adjusted to the really cold weather, and of course I haven't, because I'm now in Texas. So it's interesting when we she'll she'll say, "Oh, it's 50 degrees today. We got we're burning up," and I'm thinking, "Wow, that's a little on the cool side for us." So the weather is always an interesting conversation. Like I said before, I will have your test up tomorrow, same format. Again, same time window, available at 6 a.m. And then, of course, to the next day, Friday, Thursday and Friday, by 11 p.m. And the same, have a test work 3 tab where you'll use the Turnitin with your one file like you've been doing. And I appreciate that. That really makes the process very simple and keeps all of your work together so I can easily access it. So I appreciate your attention to that. And again, it is no small task to have to do classes online, keeping track of everything so I know what you all have to do, because I have to do it myself. And you're always checking off the little tasks as you go from one task to the next. You're like, well, I crossed that out or check it off, and then move over here, and then think, well, did I forget anything? So I appreciate your attention to that. That always is how I feel, even though I may not always say that. Now, what I wanted to do today is just cover some examples from a practice test, and also just some ideas in general that, for instance, when I get questions, I'll think, well, that's a good item to bring up in lecture. And so let's get started with that. I'll go ahead and share my screen. Now, I did receive a question yesterday that was I marked in the problem in the message. I said, "Good problem," because lots of times, you'll work on an example and you'll pretty much know what to do. It's like, well, Professor Ron talked about this, so I know I need to use this, and you get pretty much 85% of the problem done. But I wanted to mention something about this particular example, and this makes a good review example. So I'll just mark this review. So the problem looked like this. If I recall, I actually scratched it down on a sheet of paper when I was typing my response. We have n equals 2 to infinity, and then we have x to the ln of n. So when you look at this, the question said, determine the values of x for which the series converges. So this is how the prime, you probably have already worked on this, and so maybe I'm boring you, but I think it's worth saying. Determine the values of x for which the series converges. So you're looking at this and thinking, well, that kind of looks maybe that's mimicking a P series or something. I'm not sure. You look at it and you're thinking, well, is this is what we need to do? And then you have to think back. This is in section 3, integral test. So you think back to a construct that you did in Calculus 1, and that is you would always change bases to base E because the base E calculus you understood, and that's what allowed you to transfer the calculus to all the other bases if you knew base E. So first, we want to observe the following. That is, this we can rewrite X. And I thought this was an interesting problem because when I got the message, I said, oh, we have to rewrite this to make it look more like what we think it should be. And so here, we'll just say E to the ln of the power function X to the ln of n. So this is like writing the same thing twice because, of course, the natural exponential and the natural log are inverses. So this hasn't done anything except just rewritten this, couching it in with these two functions that are composed, which basically gives you the identity function. But then, of course, we know the power of logarithms, especially when we do limits. I mean, using the continuity of the logarithm in context with L'Hopital's rule is very powerful. We use that and we depend on it. Logarithms are good. It's like determinants in linear algebra. You keep them around because they're useful. So we're thinking here that we can just use the power rule. So again, the power rule, this is like, you know, what you learn in pre-cal, and of course you relearn it in Calculus 1. So this gives you E to the ln of n, and then we have times ln of x. Now, again, this is just a power rule, right? We've got a E to like the A times B, and that's just E to the A raised to the B, or, you know, parentheses to the B, using our laws of exponents. But what we're going to notice, and I'll do this will just be E to the ln of n raised to the ln of x. And it's interesting because the author of this book is a topologist, and he often gets very creative with problems. And so I thought to myself, good for Dr. Larson. And so now, of course, we see this collapses. This is just n using the inverse nature of the natural base and the natural logarithm. So this is n to the ln x. Now, I was very impressed with one of your classmates because they were able to navigate the first two parts of it very, very successfully. And so I thought, when I saw the third part of the question, I said, well, we've got to analyze this in more detail. So that's when I thought about this. And now this is looking more like the P series. Okay, so now we can take and I think there was an issue, at least when it started out. It said, what happens when, this was the first part, x equals 0, or was it, I don't know if it was x. Lucinda, what, do you remember which one it was? Which values of x did we have to check in parts A and B? Do you remember?
Let me take a look.
Yeah, thank you. I knew Lucinda's the smart student who asked about this, everybody, but she has a good memory because I knew we had to check two values of x. Like maybe a E and a 1, maybe?
I didn't think it was that. I thought it was a 1, but I
Okay, so
didn't think it was complicated.
we had x equal 1, and then we had x equal like 1 over E or something.
Oh, for the second problem?
Yeah.
Yeah, it was 1 over E.
Okay, so we had x equal 1 and then 1 over E, and then the third part was what I wrote up here, right? Which values of x does it converge?
Correct, exactly.
Okay, excellent. So Lucinda, you get 10 points. Okay, so now when we look at this part, we're thinking, okay, well, if we just look at what we have here, we say, all right, well, let's write the series with the new construct. So this is n equals 2 to infinity. Then we have n, so we have ln of 1, right? Okay, so this is neat. So now ln of 1 is 0, so this is n to the 0, and by definition, that's just 1. So we have n equals 2 to infinity of 1. Now, someone tell me what would we know about this series here? If we had to say converge or diverge, does anyone have an idea of what they might think it would be? Well, let me just give you a hint. The very important theorem is the divergence theorem. Remember, we know if a series converges, then the nth term must have limit 0. Okay, now if you flip it around to contrapositive, if you check the nth term and it doesn't have limit 0, then all bets are off. So in the contrapositive form, that's very good. So note, here's our nth term, right? And we see that the limit as n approaches infinity of 1 is what? 1, which is clearly not what? 0. All right, so this what? Diverges by the divergence test. All right, so this is actually kind of difficult in the sense that all the stuff that we've learned just kind of centers into one problem. And now for 1 over e, let's do the same thing. N equals 2 to infinity, and then we have n, and we have the natural log of 1 over e. And so let's just go ahead and use the laws of exponents. Again, this is just e to the negative 1, right? So we have n equals 2 to infinity n ln e to the negative 1. And what's the logarithm? Well, it's a power of the base. So the power of e that equals e to the minus 1 is minus 1. So we just get what we thought we would get, n equals 2 to infinity of n to the negative 1. But of course, we can write this in a more standard form, which is just 1 over n, right? Okay, so now we look at this and say, well, this is one of the series we have in our back pocket because, you know, we don't want to have to reinvent the wheel every time. This is the harmonic series, just minus a 1. And so this is a famous divergence series that we got using the integral test. So this is the harmonic series. And this diverges. So there's certain series when it comes to the P series, we just want to say, okay, we already know this and we use these really famous series for comparisons. So now we can see that all of this stuff that we worked with the integral test kind of gets pushed over into the comparisons that we did last lecture. So that really helps to illuminate things. Now so we've got these interesting deals right here. We've got two specific cases. So that was an analysis that we could use using this. Now what we can do is we can rewrite the series to make it look like a P series. So let's do it. And then I think we can answer this question just using the P series theorem. So we have n equals 2 to infinity. And so what do we have? N to the ln of x. So let's just do the same old trick that we do in general math when we try to impress everybody with our algebra. So we're going to say 1 over n to the ln x. Just say, what's 2? 1 over 2, right? So this will be n equals 2 to infinity 1 over n to the negative ln x. Because I have to admit, when I got the message that Lucinda mentioned P series, I said, oh, that's it. That's how you do it. So she actually helped me craft a solution to this. So now we see, okay, what's the deal here? This is a P series. So now we see that P is taking the place, or negative ln x takes the place of P. And we know that we have convergence And this is an interesting function because of course it's going to have to start at 0 because of the domain. The convergence in this case will work as long as P, which equals negative ln of x, is greater than 1, right? That's the theorem. P has to be bigger than 1. And that's really how we think of it, like 1 over x to the P for the P integral. It's the same thing. As long as we can keep that power in the denominator, the function doesn't blow up when we pass to infinity. So that was something that was very intuitive earlier. So now, if and only if, we'll just go ahead and multiply by -1. So we have ln of x is less than -1. And then, of course, we can apply the natural exponential, which is an increasing function, which will preserve the integral, or not the integral, the inequality. Integral inequality, they all start with n. So this will be x is less than e to the -1. So we apply e in both cases, like e, and we get this. So now this basically says that this is going to fall off and not blow up as long as we stay less than 1 over e. And then, of course, the minimum will just be the 0. Of course, the log function diverges to negative infinity. So this implies x would have to be in the domain of the logarithm as long as it's less than 1 over e. So we get 0 to the 1 over e. So this was kind of an interesting problem, basically because it communicates with the P integral and the P series. And you can see that, again, very clever, very clever. You know, I mean, I used to, back when I did a lot of courses in class, you know, we had back in the olden days when we actually met on campus, I would do an interesting problem and I'd say, well, that makes a good test question kind of thing. And they say, oh, no, don't put that on the test. We'll never get that. I said, well, I'll go home and learn this. I said, practice this, learn this. This will be good information. So what I wanted to do, and again, I thank Lucinda for her question, because there were so many nice things that we see in this. When I present problems, I try to break them down and say, well, look what we have here, how it connects to the previous problem and how we're going to use it in the future. So this problem just kind of covered lots of bases. So I thought that would just be a good summative problem with the integral test. Now, remember, the integral test has some hypotheses that we have to check, but this basically just centered around the P series and then using a construct from Calculus 1. Remember, and you know this, to convert all of the bases, we use this basic change of base formula, but you don't have to memorize it. You can just take the power function or the exponential function and do this construct and get here and use the power rule for logarithms. So when you take linear algebra, I've taught that many times, but I had a course this spring that didn't make. Everybody wanted to take it at the South Campus. I think my reputation preceded me. But the thing is that you'll study determinant functions, which for many purposes, you'll think, man, this is kind of tedious. Why do we do this? Well, the theoretical backbone of the determinant is essential for analysis. We don't use it much in Cal 1 and Cal 2, but when you get to Cal 3, it becomes extremely important. And so, and you see it in places. So it's one of those things that, kind of like the logarithm, you just kind of let it hang around because it really does give you plenty of nice mathematics. Okay, so very good. Thank you, Lucinda, for that problem. So now I want to do some other examples. And again, I got a couple of questions. I've got a practice test here. I had a couple of questions about geometric too. So I want to say a little bit about those. So here's another example. So lots of times on the test, especially when we have the first few sections, the question will say, does it converge or diverge? Okay, if it converges, can you find the sum? And in some simple cases, we can actually find the sum. So that's a good thing. So for instance, if we have something like this, n equals 1 to infinity of 4 divided by 7 to the n. Now, remember, series can come in all kinds of different packages. If we look at this, this is not in the form we're accustomed to. We're more accustomed to this, okay? So that doesn't mean that everything's going to be given to you on a silver platter, and you have to break it down and then think, well, how did Professor Ron introduce this? Does it fit the form? Can I figure out the parameters so that I can actually get to a sum? Now, when you look at this, you start to think geometric, but it's kind of odd in the sense that you've got that 4 hanging out. So we can assume convergence, and at least we think it's going to converge, but we can always do algebra. We can always factor things. We can always do algebra on a sum. It may not, provide us any information towards convergence, or we find that it diverges. That's okay. We saw that with the alternating series. So first, what we can do is say, okay, well, we've got a 4 here, which we can factor. So we have n equals 1 to infinity, and then we have 1 over 7 to the n. And then, of course, what we want to do is think about using laws of exponents. So we have 4, n equals 1 to infinity, and then we just have 1/7 to the n, okay? So when we look at this, this doesn't have the same exact form as when we derive the formula. So basically what we have to be able to do if we want to use the a divided by 1 minus r is we have to determine the a and we have to determine the r. So if that's not quite obvious to you, then write out a few terms. Don't guess. So now, again, notice what we usually do, and I can do this 2 ways. The first way, we notice that we normally start here at 1, but when I derived this, we had the n minus 1 here, okay? So in order to use that formula, I'll do it 2 ways. Here's the first method. We'll say, well, let's make it look like the formula that we derived in class. N equals 1 to infinity, and then we're going to write 1/7 times 1/7 to the n minus 1. And so now, of course, the 1/7 is just hanging out, so that's a 4/7. So we have n equals 1 to infinity. And so I'm going to write this like we had before. We have 1 times 1/7 to the n minus 1. So this basically gives us a different way of looking at it, which is comparative to the way we derived it. That is, we have the a and the r because when n is equal to 1, we just get the a, and then when n is equal to 2, we get the a times the r, and then plus the a times the r squared. So this was the form that we derived in class. So if you look at this, now you can easily say a equals 1, a equals 1, and r equals 1/7. Of course, that is if you want to derive this form. Now, the second method you may find is easier. So now this gives us 4/7, which is just hanging out right here, because this part, we know, this will just be a, which is 1, divided by 1 minus r, 1/7. So this will give us 4/7. And of course, now we have 7 over 7 minus 1/7. That gives us 6 over 7, right? And then, of course, we invert and multiply 4/7 times 7 over 6. So the 7's absorb, and that gives you 4 over 6, or 2 over 3. Now what's interesting about this technique is that it's just like what we did in class. But maybe you're thinking, well, I don't have to do it this way. I'll just look at this. So for instance, we can think of this as method 1. I do the same when I teach pre-cal. I tell the students, I said, you can use the form we derive, or you can write out a few terms and figure it out yourself. So for instance, when we get to this point here, this is where we are when we derive it. So I'll just say, here's method 2. And maybe this doesn't mean much, but I'll just say we've got 4. We have the series n equals 1 to infinity, 1/7 to the n. So now what we can do is, like, we're thinking, all right, well, this isn't exactly the form, so let's just write out a few terms. So now we have what? N is 1, we get 1/7. N equals 2. Well, we don't have an equals. Of course, we have a plus. That'd be kind of interesting. And so we have plus, so we have 1/7 squared. Then we have 1/7 cubed, etc. So that would be a way of mapping this in just writing out a few terms. So now we can look at this part with this method, and we see that the first term is 1/7. And then, of course, R is 1/7. So depending on how you write it or how you configure it, the A's can change. The R, of course, is going to be the same. So now this will give you 4. And then we have A over 1 minus R. So we have 1/7, 1 minus 1/7. So again, the 4/7, just the 1/7 just come over here with the 4. So we get 4/7. And then, of course, we get the same thing, 1 over 6/7, which is 4/7 times 7 over 6. And of course, now the 7's absorbed and we get the 4 over 6, or the 2/3. So it doesn't really matter how you configure it as long as you're consistent. Lots of times, when you were doing like the partial sums and you only had to add up a few terms of the geometric series, you really did have to consider how many terms you had before you did the partial sum. But at least with the infinite sum, we don't really have to worry about that. You just need to make sure that if you don't write the form from the derivation, that you clearly know what A is and you clearly know what R is. And so this, again, this is more pre-cal, but it really does belong in the calculus class, because the main result is that we have convergence. Well, let me write this out. Convergence. So we're looking at this, A, where n equals 1, A, R, n minus 1. Convergence, if and only if what? The absolute value of the common ratio is less than 1. And so that's a special limit. So again, don't stress about the geometric. The geometric is our friend, and we will use it so many times that you will master it. And when you get to the university and take complex variables, a lot of you who will go into electrical engineering, or some of you mechanical engineering majors will take it, you'll see again the presence of the geometric series. It's ubiquitous. It's like number theoretic constructs with the Pythagorean theorem. We enjoy the use of it because it makes our life easier. Now, one thing that's useful with the geometric is the following construction. And here's another example. We say that, remember I did the example of expressing a given repeating decimal in terms of a fraction of 2 integers. So here's an example. So express the number as the ratio of 2 integers. So let's look at this. We have 0, and then we have 3, 8, 6, 3, 8, 6, ... So basically this is 0.386 repeating. Okay. So again, there are ways to cheat to do this. And if you had a more, I'll just say this, for if you have a problem like this on the test, I do want you to use the geometric series. I mean, that's that's kind of what we've been doing. And I mentioned the fact that there might be alternative methods, but I do want you to understand the geometric series. So I would kind of insist on that. So when we look at this, we're thinking, well, let's just write down what this actually means. So what does this equal? Well, we could say this is 0.386 plus, and then tack on 3 zeros, 386, and then 6 zeros, 1, 2, 3, 4, 5, 6, 3, 8, 6. And let's just do one more for fun. So we'll have 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 6, 8. I think I did one in class where we had like a 1/5, we had a 0.2 in front of it, which didn't repeat. So that part clearly isn't geometric. But so what we're seeing here is we get a very interesting construct. That is, we've got this number repeating over and over. Now at this point, you have complete control over the algebra. For instance, if we look at this and think about what's going on, we can go ahead and factor and then use an a that's actually a fraction. It doesn't have to be 1 or something simple. We'll be in control, so to speak. So now we can say, all right, well, let's just factor 386. And then, of course, we've got the what? We've got to move the decimal 3 places. So 0.001, right? Now we've got to move it what? Let's see. In this case, we've got to go, let's see, 1, 2, 3, 4, 5, 6, right? So 1, 2, 3, 4, 5, 6. All right. And then for the next one, how many? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. So this is just doing the pounding it out with geometric series with some general math. And so now we can look at this and say, well, the A and the R will be the same. So let's write it in a way that looks a little bit more user-friendly. So we can say that this is what? 1 over 10 to the third. And now we have 10 to the third times 10 to the third. So we have 1 over 10 to the 6th. And then 1 over 10 to the 9th, etc. So where you stop is completely up to you. You don't have to work it a particular way. You have complete control here. And so now we're thinking this part is geometric series. And now we can see the first term is just 1 over 1,000. And the R, how do we get from here to here? 1 over 1,000. So we have A equals 1 over 1,000. Now you're going to think you know a lot about the geometric series. B equals 1 over 1,000. R. Tell I've been doing a lot of number theory lately. I derived a formula to generate Pythagorean triples for my pre-cal class. And so I've been thinking A's and B's, M's and N's. So now we're good to go. We've got the formula for this, and clearly this what? Converges because of the restriction on R, an absolute value less than 1. So we say convergent. So now we have 386 times, so we have what? A, which is 1 over 1,000. And then we have 1 minus R, which is 1 over 1,000. So we've got 386. And we'll move that over 1 over 1,000. And now here, of course, we have 1,000 minus 1. So that's 999 over 1,000. Now, if you want, you can go ahead and move the 1,000 over here under the 386. So 386 1,000. And then, of course, now this we invert and multiply. So we have 1,999. So, of course, the thousands absorb. And so we have 386,999. Now, one thing that's interesting here is that clearly this is divisible by 3, but you can see here, this is 14 plus 3, which is 7. And that clearly isn't divisible, 17, excuse me, that clearly is not divisible by 3. And all we get out of this is a bunch of 3s and 11s and things. So this is reduced. Now, lots of times when you look at this, you can kind of, with these types of problems, you can kind of mess with it a little bit and say, oh yeah, I can figure this out. I don't have to do this work. Well, the key here is that if you throw in a 0.2 in the front or a 0.3 in the front, that really does change the arithmetic and gives you more to do. So use this example not so much as, oh, well, you know, I could probably intuit this quicker. No, use this as an example to practice with the geometric series, because when you study more mathematics, when you study more engineering science, physics, even number theory and computer science, discrete math, the geometric progression is all over the place. You can't get away from it. So it's important to be able to navigate. So again, when you work with geometric series, if you use a formula, you must set up for the use of the formula. That is, you must have a clear A and a clear R based upon what you have written. And if it's not consistent, then you won't get an answer that makes sense for the problem you're doing. So it's not a mindless task. Unfortunately, you know, when you're teaching younger students how to solve equations, everybody wants the equation to be user-friendly. And that's just not the way it is. It never comes in a form that's user-friendly. We used to pretty much all the time, we have to change things and rewrite things to fit a particular pattern. Okay, so just think about that when you're working with the series. Now, another example, I wanted to spend some time on the series because I know this is a little bit harder for you. You're fairly decent with the integrals, but the series are hard. And of course, on the test, I'll give you plenty of practice with integrals too. So I wanted to look at a telescoping or something maybe that possibly telescopes. So we have n equals 1 to infinity, 4, and then we have n times n plus 3. Now, the nice thing about what we've already done is we've already talked about the p-series and then the comparison test. So when you think about the comparison test, you look at this and say, well, this really, the denominator here grows like n squared. The 3 times the n does have an impact for initial values of n, but as n becomes really large, the n squared dominates. So if we're thinking just a comparison test for convergence or divergence, we would think that this series converges. Okay, so, but the question here is says, determine if the series converges or diverges. If the series converges, it says find the sum. Now, what that means is that normally when you're doing something that grows like a p-series, you don't have a nice formula. You know, we saw that we can estimate series with the alternating series, and we can estimate series with the integral test to get an upper bound. I mean, we don't have the luxury of always having an exact sum. So you would think, what would be the way to cover both bases simultaneously? Well, that's just to kind of go out on a limb and say, well, if this does have a sum that we can actually get to exactly, then this would have to telescope. And that means that the terms would have to systematically absorb, and we're just left with a few terms that are simple. And so the partial sum is so easy that we can pass to the limit and magically we have the sum. So the first thing we need to do is the partial fraction decomposition. Now, on the test, I'll already tell you, you will have to use partial fraction decomposition and you will find it in integrals. And I need to see the decomposition, okay? I can't abide by seeing an integral and then magically you jump to the decomposition. It's not obvious, ladies and gentlemen. So if you figure out coefficients for the actual factors here in the denominator, then I need to see that computation, because that's how I teach you. Otherwise, it doesn't make any sense. I mean, you don't just move from one structure to the next in a magic fashion. We have to show the work. So now we can say 4, and this one's not so bad. We don't have any quadratic factors. So here we have 2 distinct linear factors. So this will be A over N plus B over N plus 3. And of course, ladies and gentlemen, this is where we're a little bit more flexible. We're thinking, partial fraction decomposition, where we usually think about a real variable, but just like doing L'Hopital's, in some cases, we just stay with the N. When we do the integral test, we usually switch to X. That's fine. There's no problem with that. It is certainly okay with me. So now we clear denominators. We know we have N times N plus 3. So this gives us 4 equals A times N plus 3 plus B times N. So these are really simple. These don't take much effort at all, but the construct is important because it gives you good practice with this, so that in cases where you've got higher powers, I've taught you how to differentiate to knock the powers down to be able to compute the coefficients. So now we can take some easy values of N. First, we'll just say N equals 0. And so we have 4 equals what? A times 0 plus 3. And of course, that's a 0 term. So if and only if 4 equals 3A, if and only if A equals 4/3. Now, of course, if this is going to telescope, then we see these are offset by 3. B would have to be the additive inverse of this, and I think we'll see that. So now N equals what? -3, a convenient value for N. So we get 4, and of course that zeroes out, and we get B times the -3, which is exactly what we need. So the big giveaway with these types of problems is that you could use the Oliver Heaviside cover-up method. I didn't really teach that because this is so straightforward, and this path allows you to differentiate if you need to and be done with everything. And you look at this and think, wow, it's really interesting how the differentiation process simplifies the problem. But when you've got these easy linear factors, this is the quickest way to get to the coefficients. So now when we look at this, we have the following. So the infinite series N equals 1 to infinity of 4 divided by N times N plus 3 can now be written as the infinite series N equals 1 to infinity. We'll use brackets. So we have 4/3 over N plus -4/3 over N plus 3. So now, if you will, we can go ahead and factor the 4/3. So we get 4/3 N equals 1 to infinity, 1 over N minus 1 over N plus 3. Now, here's where you're thinking, okay, well, this will telescope, but these are offset by 3. So we have to write out a few more terms. But how do we do that? Do we just kind of focus on this and be done with it? Well, the easiest way is just to look at the partial sum. And when we look at the partial sum, what we see is we get the telescoping effect, and then we can pass to the limit. So now we have S of N will just equal k equals 1 to n of 1 over k minus 1 over k plus 3. So what we'll do is we can write out 3 or 4 terms and then do the same for the end of the series and be able to see the telescoping. So, and of course, we got the 4/3 out here. So let Professor Ron make some room for that. 4/3. Don't forget 4/3. He's important. So 4/3. So first we'll have k equals 1. So I'll just write this down. K equals 1. So we'll have 1 minus 1/2. Then we have k equals 2. And we'll have, in this case, wouldn't that be interesting that we would get absorption that fast? 1 plus 3 is 4, I think the last time I checked. And then we have k equals 2, so we get 1/2 minus, and now 2, that's going to give us a 5. K equals 3, so now we have 1/3. And now 3 plus 4, or excuse me, 3 plus 3, that's 1/6. And then k equals 4. So we're going to get what? 1 over 4. And then we'll have minus, in this case, 1 over 4 plus 3, 1/7. So that'll keep going. So now what we can see at least here that we start absorbing when we're removed by 3, right there. Now, as we start building, notice we've got the 1/4, and then the next will be the 1/5, and then we'll have the again, they're separated by 3. We have the 1/8. So notice that we're gonna start to knock off all of these terms. So let me just write one more term here so you'll believe me. Probably stop too soon. K equals 5. So this will be 1/5, and then we have minus, and then of course we have the 1/8 as I said. Now notice with all of these numbers here, the next one's going to kill off the 1/6, but as we keep progressing here, notice the 1/3 survives because we're never going to get a negative 1/3 out of this. So we can say this is going to survive. What about the 1/2? Well, it's going to survive because again, we're never going to generate a 1/2 in the second term. So this survives. And then again, the 1/4, well, it's gone because there's there, but the 1 we're never going to generate a 1 in this second term. So this survives. So this is where when you've got a separation that's a little bit more, you have to be a little bit more clever, write out enough of these terms knowing that these are always going to be separated by 3. And these are going to build in size. And so there are going to be some initial numbers as we see the 1, the 1/2, and the 1/3 that will never absorb because this denominator will never be 1. This denominator will never be 2, and it will never be 3. Okay. But after that, 4, we're good. Gone, 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 etc. And then at the end, let's do the same thing. So we'll have an ellipsis here. So what I'll do is I'll just do k equals, we'll just say, we'll write down several. We'll say k equals n minus 3. So we have 1 over n minus 3. And now k is n minus 3, the 3's absorbed, so we just get 1 over n. K equals n minus 2, so we get 1 over n minus 2. And now we have the minus 2 and the 3, so that's an n plus 1. And then we have k equals n minus 1. So we get 1 over n minus 1. And now we have the -1 plus the 3, so that's a 2, 1 over n plus 2. And then lastly, we have k equals n. That's the easy one. We just have n and the n plus 3. So again, it takes a few more steps just to kind of see what's going on here. But now when you look at this and you think about what's going on here, notice we can start to see that things absorb. And now in the, what we can notice here, the n minus 1 here, that's going to be in the previous one. This will absorb too. So we can do like, you know, absorb. All of these, again, it's kind of interesting when we start looking at this, how things are going to go away, so to speak. So this will absorb. And now when we look at the n minus 1 here, it will, well, let me just go to this, the n plus 1. It's going to be down here a ways. Let's see. Let's just see what else we have here. So the n plus 2. Oh, wait a minute. Let me write it this way. This will be a little bit clearer. Let me get rid of this line. I'm going to go too fast. So now, let me say it this way. We see that these absorb here. And then when we look at this, the n minus 1, that's really what I wanted to do. When we back up here, we have the n that absorbs with this. And then as we move up 1 here, the next term will have the n minus 1. So this will absorb. So let me just say absorb. And then as we back up again, this will absorb. And as we back up again, this will absorb. Now one thing that we notice, and that's interesting about all of this, notice here, we get the same thing we have up here. These terms here don't have any counterpart with the additive inverse. See, this would require an n plus 1, but this is never going to be an n plus 1. So again, this survives, just like we had up here. This survives. This survives. Again, we would have to have a counter of this with a plus 1 over n plus 3. That's never going to be n plus 3 because the biggest n can be here is n. So these survive like these survive. So the reason I wanted to do this is because the separation is bigger, we have to look for 3 surviving terms. When we have 1 separation, we have much fewer, actually 1 on each end. So now what does this equal? So we have 4/3. So we've got 1. We have plus 1/2 plus 1/3. And then we've got our stragglers at the end, minus 1 over n plus 1, minus 1 over n plus 2, and minus 1 over n plus 3. Now we can pass to the limit. So this is easy. Well, easier than it was before. So now we say the limit as n approaches infinity of s sub n. And now, of course, the only thing that survives, these are all 0. So we get 4/3 times 1 plus 1/2 plus 1/3. And of course, 0, 0, 0. So we're stuck with a bunch of zeros. So let's get a common denominator, 4/3. So we have a 6. So again, we get a 6 here. So we got a 3 and then a 2. So we have 4/3. And then of course here we have a 5 plus a 6, which is an 11 over what, 6. Again, the 2's absorbed, so we get 2 over 3 times 11 over 3. And we get 22, in this case, over 9. So the problem itself is easy. The easier problem would be is if I gave you this to start with. if I gave you a series that was already broken up and you can say, oh, thank you, Professor Ron, this is already telescoping. I don't have any work to do. So the thing about it is that if I give you a problem like that, you're going to think, well, that's really an odd looking problem. I don't know what to do. If I give you this problem, then you know what to do. So be wary that, or very vigilant that when you look at a problem, you're thinking, okay, what kind of pattern do I see here? If I just start thinking about a few terms, do I get these terms that start to absorb in a systematic way? The key here is that the convergence we can do easily, thinking maybe either comparison test or limit comparison test from our last lecture. But the main thing is that if we're asked to find a sum, we know that that avenue doesn't give us the precise sum unless maybe we've studied a little bit of Fourier analysis, and that's beyond the scope of the course at this point. So when we look at it this way, we're thinking, okay, we'll do a partial fraction decomposition. We'll see that we get a telescoping sum, but we have to do a little bit more work. Now, of course, you can see that the terms down here as n passes to infinity, they're going to go to zero. But again, we still want to make sure that we've set up our construction carefully. And then, of course, we have to write out enough terms, again, separation by 3, to show the fact that we're going to have 3 surviving terms at the front of the partial sum and 3 surviving terms at the end. You can try to come up with all kinds of formulas and rules and things, but that gets a little bit difficult. It's easier just to write out enough terms so you can see what's going on. And so that's why, as I've done here, I write down the actual index so it's easy kind of to check things, and then you can look back and make sure that these are indeed correct. So just remember, not all series have to be difficult. Not all series have to be arduous, but when it comes to finding the sum of a series, usually all we can do is give a very, very nice approximation. The ability to find an exact sum for an infinite series is usually not something that we can do readily. So again, just remember that this is a luxury. The geometric series is a luxury, very much a luxury. I mean, because we're lucky that we get to use it a lot. Okay, so those are interesting problems. Now, on the next page here, I wanted to look at a couple of sequences. Let's see here. So here's an example. Now remember, with the sequences, you can think L'Hopital's rule, where we still have real valued functions. And then of course, with the sequences, you can just go ahead and use L'Hopital's rule again and not necessarily convert to the real variable like I've done in class. But here's a nice example. So we have x passing to infinity. This is like one of our special limits, so to speak. So we've got the limit as x passes to infinity of 1 plus 3 divided by x to the 4th power raised to the x power. Now again, for instance, if I do a problem, if we've derived a problem in class, like an integral formula, I'm okay if you use that. Let me just remind you, let me just show you. Remember, we had, and I had a typo after I had derived it one time, and I made that note on the videos. We had this. And they can be written many different ways and still be equivalent. Now, I derived this using partial fractions, and let me show you that this is in, I was working with one of your colleagues. This particular one is actually a derivative of another one that we've done, and this is using inverse hyperbolic like you did in calculus 1. So you can write it this way. That is, you can write this as 1 over 2a natural log a plus u divided by a minus u. Okay? So the idea here is that if you wanted to, you can flip things around because of the absolute value. So that doesn't change the answer. Now, of course, if you had the negative of this, and see, we've derived this. So if you come up against this in a problem, you can use it because I derived that in class. And this is a hint. The other one that comes up a lot all the time is just the additive inverse of this integrand, u squared minus a squared. So again, if you run the negative through here, so this is just the additive inverse of this. So we'll just keep the same kind of C, be sloppy. So this will be using the power rule, running this up and flipping this. This will be 1 over 2a natural log a minus u over a plus u, just kind of putting the a first. Now, in your integral table, they flip the u and the a around upstairs, which is completely equivalent because of the absolute value. So you can write it this way, u minus a over u plus a, or a minus u over a plus u, which is usually the way I write it. Doesn't matter, they're equivalent due to the absolute value. So since I have derived this in class and it comes up so much, if you see this in a problem, then you can use it, okay? If it's a formula that I have derived, fine. And if I ask you to do an integral and I don't say use an integral table, then I want you to compute it. But of course, if you come up against either of these are standard integrals and you use them. You use this. This saves you some time. Okay. And the derivation with the partial fraction decomposition is simple. They're just two linear factors. So you use this to good help. I just wanted to make that comment because I use these integrals all the time. And I don't want you to feel like you have to reinvent the wheel. But of course, if you've got to do an integral and it doesn't say use an integral table, I would like to see the computation. Okay. So I just wanted to make that comment because I was thinking about this as I was making out the test. Now, for this particular example, if you look at this, you're thinking, okay, as x passes to infinity, this is basically going to converge to 1. So we have 1 to the infinity, which we really don't understand. This is indeterminate. Indeterminate. So what's the standard technique? I mean, if we take logarithms, because with the logarithm, we can convert it to either 0 over 0 or infinity over infinity and apply L'Hopital's rule. So what we do is we set this equal to y and then take natural logs. So this is a standard technique. And of course, you'll see this on the test because I've used it many times. So now we have the natural log of y equals, and use the continuity, run the limit, the logarithm through the limit as x approaches infinity. So we have the natural log of 1 plus 3 over x to the 4th to the x power. And now, of course, our famous laws of exponents or our power rule. So this gives us the limit as x approaches infinity of, in this case, x times the natural log of 1 plus 3 over x to the 4th. Now, if you like, well, I'll rewrite that eventually. Don't worry about it now. And so now we look at this and say, well, we need to rig this so we can apply L'Hopital's rule. So we're going to put this in the denominator because we can see as x approaches infinity, this converges to log of 1, which is 0. So we need that in the denominator too. So now we rig it. So x approaches infinity, ln 1 plus 3 times x to the negative 4. I'll just write it that way. Maybe I won't even need it, but thinking maybe I do. And then just x to the minus 1. Now, when we look at this, 1 over x basically, as x approaches infinity, converges to 0. And of course, log of 1 or something, log of 1 plus a little bit converges to 0 also. So now we see this is actually indeterminate as a hypothesis for L'Hopital's rule. So now we can do L'Hopital. So yeah, I'm sure in Calculus 1, you're thinking, well, this certainly would have been very useful. So again, remember, you always have the choice of doing a factoring technique or using L'Hopital. I'm not going to be put out by that. I don't care if you don't use L'Hopital. There'll be cases where you'll have to use it. But if I say use L'Hopital, but you can come up with a factoring formula that you used in Calculus 1, I don't care. That's a legitimate process. I won't have an issue with that. So now we're going to take the reciprocal. So we have 1 over 1 plus 3 times x to the negative 4 times the derivative. And that'll just be what? A negative 12 x to the negative 5. So we reciprocate the argument and then multiply by the derivative of the argument. And then, of course, downstairs, we just get what? Negative x to the negative 2. So let's clean this up. So we get the limit as x approaches infinity. And so we have 1 over 1 plus 3 times x to the negative 4. And then we have times minus, we just do minus 12 over x to the 5th. And then we have negative 1 x squared, writing it that way so it's a little bit more user-friendly. So now let's clean this up. So the negatives are going to absorb. So we have the limit as x approaches infinity, forgive me. So we have, again, we've got a negative here and a negative, so these absorb. Put a little box around them. So this gives us 1 divided by 1 plus 3x to the negative 4. And then we have times 12 over x to the 5th times x squared over 1. So just invert and multiply. So again, this will give us the limit as x approaches infinity. So now we have a 12 upstairs. And we have a 1 plus 3 times x to the negative 4. And then, of course, the squareds absorb, and we're left with a 3. So we have an x cubed. So now we can pass to the limit because we have something that is now determinate. Again, you can factor the 12 if you want, but notice we got what we actually need. As we pass to the limit, this just approaches 1, but this becomes infinite. So this limit is actually 0. So now this is determinate. Determinate. And this limit is easily 0, just using the power of 3 of the power function in the denominator. So again, the power of L'Hopital's rule allows us to convert to a limit at infinity, especially when x is passing to infinity, that reminds us of Calculus 1. So we see that the dominant power here, this is 1, this dominates, this becomes infinite, this is fixed, so this limit is 0. And so therefore, if and only if log y equals 0, the log y is already up here, so I'll write it again clearly. And then, what's a logarithm? Power of the base. So y equals e to the 0, which is 1. And therefore, the limit is indeed 1, which you kind of expected. So of course, I will test you on this technique because it is an important technique. And I'll just say this, this is something you don't forget. Where we're using the calculus and the nice identities of the logarithm to do computations that just turn out to be very, very nice. And Again, just remember, use your basic calculus one, not anything difficult. L'Hopital's rule is on your side, so to speak, and a very, very useful rule. Okay, so that's a good example. And of course, no, I will test you on this, just like partial fraction decomposition. That's a mainstay. So let's look at some more of these. Let's see, here we go. Here's another example. Here's a limit. So these are the indeterminate forms. So we have x approaches infinity of the natural log, or interesting, another logarithm, x to the 156 over x. So this looks, intimidating, but of course it's very simple. So when we look at this, we're like, okay, the first thing we're going to do is use the power rule, because we don't care about the 156 because it just becomes a coefficient. So the first thing is, don't ignore the e's here. We love the power rule. So this is just 156 times the natural log of x divided by x. So of course we can factor the 156. So we have the limit as x, in this case, approaches infinity of ln of x over x. So this is now an easy L'Hopital's rule. So as x passes to infinity, these are both infinite. So we just have the infinity over infinity. So this is very straightforward. But again, an easy problem if we just react to the identities of the natural log or of the logarithm. So by L'Hopital, we get 156, the limit, as x approaches infinity. So we'll take the derivative. We see this a lot when we're doing sequences. We did this last class with the limit comparison test. So we have 1 over x and 1. So this is 156 times the limit as x approaches infinity of what? 1 over x. And of course, that's just like the last problem. This converges to 0. So we just get 156 times 0, which is 0. So again, we find that L'Hopital's rule is kind of that linchpin. It's the gap that we have. We take Cal 1, we're like, well, how are we ever going to do that limit? I mean, we need more structure. And so the L'Hopital's rule provides, it's kind of like the dx over x fills in the gap of the power rule. You can't use the power rule for x to the minus 1. It's not defined. And so the dx over x comes in, the definition of the natural log, boom, there it is. And then, of course, L'Hopital's rule fills in the gap that our algebraic methods don't cover. So now, let's look at an example that applies this to a sequence. So we have, let's see, it says, determine whether the sequence converges or diverges. If it converges, find the limit. Well, you know what that means. That just says process, just like we did here. So we have a sub n equals 8 plus -1 to the n divided by, in this case, 8. So we found that monotonic sequences that were bounded turned out to be really useful because they converge, and we use that to prove series or convergence tests for series. So when we look at a problem like this, we're like, okay, what's the limit? And then when we look at it, we're thinking, well, this is kind of strange because we're getting something that doesn't really apply any of the previous things. So we look at this a little bit differently. Notice when you have this particular setup, this is a time when you don't necessarily pass to the limit because it's not going to give you anything that makes any sense. So we see that this alternates, right? So let's just write down some terms. So we'll say limit. Does it have a limit? Question mark. So first, let's just do this. We'll just say a sub 1 is 8 minus 1. Okay, so we have -1 to the first power over 8. So that's 7/8, okay? All right, so that's clear. What about a sub 2? Well, now, of course, if we square the -1, we just get 1. So we get 8 plus 1 over 8, which is 9 over 8. All right, okay, well, increasing, I don't know. So a sub 3. So now we replace n with 3, but now we're back to the 1 case because this is just going to alternate. So we get 8 minus 1 over 8, which is 7/8. And then, of course, now you can see a sub 4, we'll be raising that to the 4th power, and we get 8 plus 1 over 8, which is 9 over 8. So what we're seeing here is that this clearly doesn't converge because it basically is alternating between two positive values. So now with this, we can say the following: if and only if a sub, let's just say this, how can I write this? I'll write this as a sub 2n minus 1 equals 7/8 for n element of the natural numbers. So that would start with 1. That'll give us 2n minus 1, or 2 minus 1, which is 1. And then a sub 2n equals 9 over 8 for n element of the natural numbers. Okay, well, what we're seeing here is that this sequence actually has two convergent subsequences. So for instance, the even terms are all 7/8. So that's a convergent sequence if that's all it was. The odd terms give you 9 over 8. That's a constant sequence. So that would converge if that's all it were. So the idea here is that this limit does not exist, because if the limit exists, it's unique. And then what it would mean is that for any epsilon, we would be able to find an n if we go far enough out into the sequence that we would be able to see that the terms get closer and closer and closer to that limit. But we see that we're always going to have this gap of 2/8 or 1/4. So we can never diminish that arbitrarily small. So when you think about the limit of a sequence, what will have to happen is that as we let n pass to infinity, the actual values of the output of the sequence get closer and closer and closer to some unique number, and that can never happen. So this implies limit does not exist. So you don't have to actually do a limiting construct. You just, and this is very useful. What's important about this, there's a theorem in real analysis that it says every bounded infinite sequence has at least one limit point. That's the Bolzano-Weierstrass theorem. And basically what it says, if you've got a sequence and the output is bounded, okay, somewhere in that sequence, there is a subsequence that converges. And so this is a good example of that. We see that we've got this bounded sequence. It's bounded here. We can just say it's bounded between 1/2 and 1/2 and 2, so to speak. That includes these numbers. So the sequence can't go outside of those constraints. And there are infinitely many terms. So the idea is that you can construct a convergent subsequence, and we don't have to construct it here. We can see it. We can see this subsequence of 7/8, 7/8, 7/8, 7/8, 7/8 clearly converges. We can see that this subsequence of 9/8, 9/8, 9/8, 9/8 clearly converges. Constant sequences converge. I mean, it's like when you were in calculus 1, what's the limit as x approaches 1 of 5? You know, you say, oh, it's 5. Well, the limit of a constant is said constant. Basically, that's just saying that the function does not depend on the variable, okay? So it doesn't change. So again, just remember that if you have an interesting situation, especially where you've got an alternation of sign, this should make you think about the alternating series test. And then, of course, if we set this up as a infinite series, that would really crash and burn, right? I mean, you know, that's like clearly this limit doesn't exist, so we can't do anything with this. So don't look at a series and start to do lots of work until you make sure that the divergence test is not working against you. Because if it is, then you have no more work to do. So just remember, if you look at that nth term and you can say, wait a minute, that doesn't converge to 0. That converges to 1. It's like adding 1 to itself infinitely many times. You're not going anywhere. That's gonna diverge. And we've already seen, ladies and gentlemen, and this is how you know this is true. We've already seen the following. N equals 1 to infinity, 1 over n. The fact that 1 over n, nth term goes to 0, says nothing about the convergence. Nothing, absolutely nothing. We know this diverges. This is the harmonic series. But again, it's not the theorem. That is, if the nth term converges to something other than 0, you're done. That diverges. But if you look at the nth term here and say, oh, that has a limit 0, it converges. No, that's patently false. That says nothing, because this is your example that just shoots that down completely. So just remember, if you have an nth term that does not converge to 0, then you're done. That series diverges, because basically what's happening is that you can't add infinitely many terms that aren't getting small fast enough, that is converging to 0. It's never going to happen. And what we're seeing here is that 1 over n doesn't get small fast enough. But if we just crank up the power, say a little bit, so we see 1 over n to the 3/2, the p series, boom, it converges. So if we can crank this power up a little bit, that's why we have the p greater than 1, boom, with the integral test, we get the what? We get the convergence. So this is the mystery of convergence when it comes to real series. And this will confound you. So you put this on your note card and write beside it the divergence test, that in complete detail, so you can utilize this. This is a very important result. And it's kind of the linchpin of what that drives all of us. Of course, if we want to use the limit comparison test and we have a nth term that grows like this, then we think it diverges and we do the limit comparison and we're done. So this is a very important result. Now, what about, of course, my friend is L'Hopital's rule. What about this example? So we have the limit, and it says find the limit of the sequence or state that it converges. So we have the limit as n approaches infinity. I'll write this a little bit differently. Sine of n divided by n squared. Okay, well, when we look at that and we think about it, this is similar to what we've talked about in Calculus 1. So first off, we think, okay, when n gets large, we know that n squared gets fairly large, and we're thinking, well, sine n is bounded. Okay, it's bounded. So is that going to impact convergence or lack of convergence? So what we want to do is note the following, that sine n, again, we just go to the real analysis. Sine x lives between 1 and -1. Please tell that to my pre-calculus students. Sine x lives between -1 and 1. So if we restrict to the natural numbers, which we do all the time, if we got a limit in the reals, we can apply that to the limit with the naturals just by restricting. That's no way. But again, that direction works. Going in the opposite direction can blow up in our faces. But going from the real variable to the natural numbers is correct. So here we have this. Okay, so we always work with inequalities, especially I'm glad we talked about the comparison test because this kind of helps this make more sense. And so now you're thinking, all right, well, let's just go ahead and apply the 1 over n squared because we have an inequality that we can preserve. So now if we look at this, let's just multiply the inequality by 1 over n squared. So we have negative 1 over n squared less than or equal to sine n divided by n squared less than or equal to 1 over n squared. And now the limit as n approaches infinity of 1 over n squared, well, that's just calculus 1, that's 0. And likewise, the limit as n approaches infinity of negative 1 over n squared, again, is also 0. So this implies that by the squeeze theorem, this implies that the limit as n approaches infinity, just the same as we use in calculus 1. So this is the same problem, n squared must also be 0 by squeeze theorem. So this is a really popular construct. Sines and cosines are not always the most user-friendly. We've already seen that with the Weierstrass substitution. So just remember that when you get these sequences that don't just say, okay, use L'Hopital's rule, please. Use L'Hopital's theorem. You have to look at them a little bit more analytically. They're not overly difficult, but sometimes you can make some mistakes in analysis by overlooking something that's very straightforward. So always think of the fact, okay, if I've got a numerator that's bounded and the denominator is becoming infinite, then that's probably telling me that I'm going to have a limit. So I need to think about, okay, can I bound this? Can I get a nice bound and apply the squeeze theorem? So that's a nice construct. Okay, now let's look at some integrals. I like improper integrals. That of course will be tested on your test because I think those are fun and worth your time. So example, and then I'm going to do a Laplace. So we have improper integral. So again, same as before, converge or diverge. Adjust this. There we go. So we have 2 dx over 36 plus x squared. Now, of course, if you have an improper integral and you have to apply the partial fraction decomposition, don't be afraid of it because I like the partial fraction. I did that differentiation technique with you and it's tried and true. And it is an effective tool. So I will expect you to be able to use that on the test. So now when you look at this, we think, okay, well, this is certainly an integral. That's a form that we learned the first week of class, the inverse tangent. But now, of course, this is improper because the upper limit is infinity. So we look at this as having to be rigged into a limit that respects the integration process that we learned in calculus 1. So this will be the limit as, in this case, we'll just say b passes to infinity of 0 to b of 2 dx over 6 squared plus x squared. And so now, of course, if we look at this, we're thinking, okay, well, a is equal to 6 and u is equal to x and du equals dx. So now we can apply that. So of course we need to factor the 2 since it's not part of the differential. So we'll get the 2 times the limit as b approaches infinity. Now, of course, I'll go ahead and write this and then I'll integrate it. So we have dx over 6 squared plus x squared, and that's the inverse tangent. So we get 2 times the limit as b approaches infinity. So of course we have 1 over a, so we get 1 over 6 times the inverse tangent of x divided by 6 x over a, u over a, 0 to b. So now, of course, we can factor the 1/6. So we get 2 over 6 limit as b approaches infinity. And then, of course, here we have inverse tangent of b over 6 minus inverse tangent of what? 0 over 6 is just 0. And of course, the inverse tangent is bounded above by pi over 2. So this gives us 1/3 limit as b approaches infinity. And of course, now as b approaches infinity, the upper bound is pi over 2. So this gives us pi over 2 minus, and of course, the inverse tangent of 0 is 0. Oh, well, so I went ahead and computed the limit. So I'll just leave this part out. Don't need to write it again. I decided I would compute it, but I'd already written the limit part. So this will give us 1/3 times pi over 2, which is pi over 6. So again, just remember, if you have to apply partial fraction decomposition, don't be afraid of it. It's a nice process. And then, of course, remember to do all of your work, put everything together, do all the integration process, apply any algebra or whatever you need to do, and then pass to the limit. Because again, you don't want to jump to the limit before you've done the work. I mean, we've got to process the integral and then pass to the limit once it makes sense to do so. And so that certainly can involve more manipulation in cases. And as we see here, we have to get completely to a form that we can analyze. And what's nice about an inverse tangent is your friend. What's nice about the inverse tangent is that it's a nice bounded function. And so we don't have to worry about it. We're good to go. And it's an easy function. It makes a nice probability distribution function. It's easy to note the form. So it is truly our friend. Okay, let's try another one. Now, one that I have here, of course, the infinite limits occur the most in your work, especially with the transform methods, when I gave you the definition of the Laplace and the Fourier transform. But of course, you can have infinite discontinuities, which, will occur, but you just don't see them as much. So we have 6 over the square root of 3 as an upper limit and 3 as a lower limit. And we have, in this case, dt. I thought I'd throw this one in. This is another inverse trig form, which is fun. T squared minus 9. So sometimes, especially when we do parametric equations and things, we can get sloppy about the existence of infinite discontinuities and still be okay. But it's still, even if we are being sloppy, we need to make sure that we did it, recognize it, and show that we actually get the same result being sloppy. And that's something we need to not do. And of course, as mathematicians and even as physicists tend to abuse notation pretty severely. But in this particular case, what we can see is that for this particular interval of integration, we have an infinite discontinuity at 3. So now if we look at this, we've got a 3 here. And as we approach from the right, this becomes infinite. So that's improper. So now what we can do is write the limit. And notice also here, when we square this, we just get what, 36 over 3 in that case. And so that's just 12. So that makes perfect sense. So we don't have an issue there. So, it's good to check that too, but we only have one problem. So we have, in this case, we can use A approaches 3 from the right of the integral A to 6 over square root 3 dt t square root t squared minus 3 squared. Now, of course, this is the inverse secant form. And what we need to do, again, is like we did in the previous example, is go ahead and evaluate this and then pass to the limit. So we can use our inverse secant form. Again, notice here, A equals 3, U equals T. How nice, du equals dt. So we like that. Don't always count on that, but you know, we make adjustments if we need to. So now this will be the limit as A approaches 3 from the right of now we have 1 over A. So we have 1 over 3 inverse secant of the absolute value of U, so absolute value of T, divided by 3. So you can write it that way. Evaluate, excuse me, between A and 6 over the square root of 3. So now let's apply the fundamental theorem. So we have the limit as A approaches 3 from the right. And if you like, we can go ahead and factor the 1/3. So just go ahead and move this off to the left. 1/3 the limit as A approaches 3 from the right. Apply the fundamental theorem. So we have inverse secant. So we have, in this case, 6 over root 3. So the root 3 can join the 3 downstairs. Absolute value, of course, is what it is. So we have 3 root 3. Then we have minus inverse secant. In this course, we have absolute value of A being positive in this case. It's approaching 3 from the right. So this will just be A over 3. So now we have 1/3, the limit as A approaches 3 from the right. So now we have inverse secant. Now notice the 3 absorbs into the 6 to give us a 2. So we have 2 over root 3. So these are nice numbers on the unit circle. So, you know, we don't always get them, but if you need to write an exact, and just leave it alone. Don't worry about it if it's not on the unit circle. Then we have minus inverse secant of A over 3. Now we have simplified this to the point where it makes sense to pass to the limit. Again, just like we always do with improper integrals. So now we have 1/3 limit. Well, and of course, I'll talk about limits, but we're passing to the limit now. So let's go ahead and see what we get. So now, of course, remember, inverse secant of X, this is why we defined it this way, is cosine of the inverse inverse cosine of 1 over X. This is the reciprocal rule. I teach this in pre-cal. Of course, you all get this again in calculus, reciprocal rule. So this is just going to be inverse cosine of root 3 over 2, just to put it in more user-friendly form. And of course, A is approaching 3 from the right, so this ratio approaches 1. So we have inverse secant. Well, and we might as well go ahead, that's a 1. Let's go ahead and just write it with inverse cosine. 1 over 1 is 1, so inverse cosine of 1. So remember, the inverse cosine, where does it live? Between pi and what? 0. So now we have 1/3. So inverse cosine of root 3 over 2 is just pi over 6. And of course, the inverse cosine of 1 is 0. That's on this end. And now what's interesting about this particular problem is that if we compare it to the last one, we're doing the same. We just get to review some of the stuff that we did the very first day of class. And so this is going to be what, excuse me, 1/3 times pi over 6, which is pi over 18. So one thing that's important about doing analysis or calculus is just respecting what we've already done. And you can see here, again, when you prepare for this test, it's probably best to focus on the things that you do least well. If it's the series, spend time on that. If it's the sequences, spend time on that. We've done so much integration that I think you're, like I say, you're fairly adept at doing that. Now, I have one more example that I want to look at. And I just want to remind you of the technique for the partial fraction decomposition, because this is kind of fun. And here's an example of it. And I just want to do the decomposition. You can finish the integral, but here's an example of decomposition. Example of partial fraction decomposition. One of my favorites. I appreciate your WebAssign questions because they kind of help me to fashion some of what I do in the review, because I know what you have questions about, and it helps me to say, okay, I'll just go ahead and throw this in. So thank you for your WebAssign messages. So here's a decomposition. We have 3x squared. I just want to review it. Plus x plus 5. And then, of course, remember factoring. If you have a denominator that can be factored, then you'll need to factor it. And it may give you a what? It may give you a linear and a quadratic, like a sum of cubes or difference of cubes. That's always a nice example for partial fraction decomposition. So when you look at this, we have 3x squared plus x plus 5, and we have x squared plus 3 times x minus 4 in the denominator. So if you wanted to try to integrate this, you're thinking, well, I've got to decompose this into some simpler factors so that I have a quadratic factor and so that I have a linear factor. So then I can apply the techniques from calculus 1 or calculus 2. So the idea here is that I just want to review the construct of doing differentiation to remind you of that. So now, of course, what we can say is we'll take our linear factor. This will be a over x minus 4. And then we have our irreducible quadratic. So we need a bx plus a c divided by x squared plus 3. So remember, decomposition is just college algebra backwards. If you were doing this in college algebra to get the common denominator, you'd say the LCD is this times this, and you've got that, and then collect your terms. So when you go backwards, you basically just have to represent the distinct factors in the denominator and work backwards. So this is something you've done, but you always did it, getting a common denominator. You never went to the backwards process, but it should not be at all confusing, or at least mysterious, as to why we have to do this. This is just undoing, decomposing, so to speak, the fraction. So now if and only if, let's make it simple. Let's clear denominators. So we get 3x squared plus x plus 5 equals a times x squared plus 3 plus bx plus c times x minus 4. So now first, because it's simple, we can just go ahead and figure out a, because we can zero this out with a 4. So let's go ahead and do that first, then we'll differentiate. So we'll say x equals 4. So this number is a little bit bigger, but we can do it. So we have 3. So 4 squared is going to be a 16. So we have 3 times 16 plus 4 plus 5 equals, now of course this will zero out. So we'll have a And we'll have what? A 16 plus a 3. So 16 plus 3. So let's add this up. This is 48 plus 9, and that gives us a 57. So now you see it. This is 19 times 3. Hallelujah. At least we got some nice numbers. So A times 19. Well, that was easy enough. So of course, A is 3, right? If and only if A equals 3. So that's how you do it when you've got a linear factor. You just pick an easy number that zeroes out something convenient and allows you to solve for A. So now we can go back and fill that in. So we have 3x squared plus x plus 5 equals, now we can put in 3 for A, 3x squared, and 3 times 3, that's a 9, plus a 9, and multiply this out. So bx squared, and then we have bx times a negative 4, so negative 4bx. Now multiply by c, plus cx minus 4c. Okay, so instead of having to do some hideous algebra, we just differentiate, because now we have a nice equation that's differentiable. So let's differentiate. So now we'll get a 6x plus a 1. That's a 0, of course. And oh, well, here, let me wait a second. Let me do something. We don't need to notice here, and I didn't even recognize this. Look, we got extra here. These are extra. They're gone. So let's just see if we got any other extra. No, everything's cool. We could reduce that, but we won't do it. So now we have a simpler equation. Let's go ahead and get rid of that's a waste of time. So x plus 5 equals 9 plus bx squared minus 4bx plus cx minus 4c. I mean, if it's gone, just get rid of it. Now we'll differentiate. That's because we're lazy. So now this will give us a 1. Of course, that's a 0. Then we get a 0. So we get a 2bx minus 4b plus c. And of course, that's a 0. Now differentiate again. So now we get 0 equals what? 2b. And these are 0, so b is 0. And now if b is 0, we can go back up here. So then we have 1 equals, in this equation, we have 1 equals what? 0 minus 0 plus c. So c is 1. So then 3x squared plus x plus 5. And let's see here. Here we go. So we get x squared plus 3 times x minus 4 equals, so we have a, we have 3 over x minus 4, and then we have plus 1 over x squared plus 3. So this is what I wanted to show you, because again, when you do your test and you work at some of this, it's important to be able to look at this and say, okay, if I've got quadratic factors, how do I navigate all of this algebra? Because now you've got two simple integrals, or maybe you have to manipulate a little bit, because you've got to work the du and the u and then break it up into a simpler integral or whatever. What we notice here is that the power of differentiation makes this problem very easy. And it's interesting, when I started teaching calculus 2 at San Jac, even when I was at Texas A&M as a grad student, the students would say, man, this is hard. I don't like this partial fraction decomposition. And I said, well, I said, you're looking at it as some huge matrix equation. I said, you're sitting there and you're trying to do everything like you did in college algebra, which is insane. Okay. In calculus, we have the use of algebra, and then we also have the use of the calculus. So one of your classmates was saying, man, that differentiation is wild. And it is. So once you exhaust the linear factors here using a simple value of X, go ahead and differentiate. And then as you differentiate and clear everything out and solve for one, then you can go back to an equation and fill that in and solve for the other variables with much, much less work, because differentiating polynomials is easy. But when you start uh, comparing everything and setting up equations, that's hard. Now, there might be instances where even when you differentiate, you still have lots of things to consider depending on how many terms you have. But that's always simpler than trying to solve some long-winded system of equations, which is absolutely a waste of time. So again, I'm a big fan of efficient work. I'm not a big fan of work that you don't do. So again, as you work your test and you work your problems, work your problems out. Again, support your answers in a legitimate way, just like I do as I lecture. And one thing I've always noticed about the calculus sequence in my teaching at San Jac is that I'm aware of what you will encounter at the university. Any math professor who has attended a major university, and I've attended too, the University of North Carolina and Texas A&M at College Station. We know what you will be up against. I taught the students who want to be engineers at Texas A&M, and unfortunately, many of them would not be able to move on. And it wasn't because they didn't possess the intelligence. It's just that they were so surprised by the amount of work. This is so hard. Why do I have to do all this work? Well, ladies and gentlemen, if I were saying, oh, this is easy and this is all you have to do, you get to the university and you take your first engineering class and you wouldn't pass. Take it from me that my former students who have done the work and moved on to the university, they say, remind your students to work hard, because when you get to the university, you have to know everything you learned at San Jac, and then they're going to pile on a bunch of other stuff. And if you're struggling with the prerequisites, then it's not going to happen for you. So being mad at your math professor is not the key. You should be happy that I know what you need and that I'm making you work so that you can have the success that you want. And just remember, everyone, with our pandemic, everybody is reformulating what they want to do with their lives. Everybody's jumping to technology. Everybody's jumping to STEM. And the competition is getting more and more intense. So the only way that you can spare yourself the agony of having to change your major is to work, and to work consistently. Just like I tell my pre-cal kids, you think of all the pre-cal that we have to use when we do these problems. It's like, where'd the calculus go? Where'd the calculus go? Well, fortunately, we did a little calculus right there. So just remember this as you do your work, that there is a reason for it and that you're building your foundation. Okay, so like I said last semester, I didn't do reviews, but like I say, if I bored you half the time, I apologize for that. I try to focus on concepts that I think you need to see. But practice, 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 and like I say, I'll have the test ready tomorrow, so you can do your test on Thursday or Friday. And remember, Friday by 11 p.m. Is the cutoff. So thanks for your attendance today. I hope everybody's doing well. If you need to take a nap, please take a nap, give yourself some rest, and take care of yourself. And good luck as you test. And for all of you all that will be doing some celebrating with your family and all, I hope that is very pleasant. Professor Ryan will certainly be busy with music. So you all have a great day, and I wish you well on your test. Thank you.